All right, we're ready to tackle Unit 2. We're going to do this first section a little bit differently. We're going to be talking about what a solution is, and you may have a pretty good grasp of this, but we're now to the point where we've solved lots of different equations and inequalities, and a solution has some fundamental properties that we want to kind of identify as we go through and look at these different types. So if we take a look at this first set of problems, it says find a solution for each equation or inequality, graph your solution on a number line. So we do need to graph these even if it's a problem like this one right here. So on number 1, we would just add 8 to both sides. We'd get x equals 11. We'd circle that. Now graphing this might seem a little bit silly. I'm going to put 0 here. The only solution on this number line, the only number that makes that inequality true is that equation true is just 11. So I'm going to make it look like that. This one, however, is an inequality, so we're going to go ahead and add 6 to both sides. We get 4x is greater than or equal to 16. We're going to divide both sides by 4, so we're going to get x is greater than or equal to 4. We're going to circle that, and then we're going to draw what this would look like. So 0 would be here, 4 would be right here. We are going to fill that in, and then we just need to figure out whether we shade to the left or the right. X is greater than or equal to 4. X is bigger than or equal to 4, so we're going to shade this direction right here. So we've got that. Now, just for the heck of it, I'm going to write this in interval notation. So that's going to be 4 to infinity. Didn't say you had to do that, but not a bad idea. Notice that when we solve this compound inequality, the word that connects those is and. It's underlined. We've got to keep that straight. When I solve this, we end up dividing both sides by 5. So we end up with x is greater than -2. And at the same time, we need this to be true. So if I solve that, I'm going to subtract 4. So we end up with x is less than or equal to 8. Now, we could leave it this way. It might be better if we graph this and then kind of check to see what the answer was and can we write this a different way. So I'm going to put -2 right here and I'm going to circle that. And I'm going to put 8 right here and I'm going to circle that. The 2 does not get filled in, but the 8 does. And then let's think about how we'd shade this. So the answers here have to be bigger than -2. So that's going to be shading this way. And the answers on this one, x has to be less than or equal to 8. So that's going to be shading this way. And remember, the word and means both. So it needs both types of shading. We're looking for the overlap here. So this is what we're looking for. I'll go ahead and erase that. And we're looking for this region right in here. Okay, so I'll go ahead and shade that. So we could write that as an inequality. We could say, look, x is greater than -2, and at the same time it is less than or equal to 8. That's probably the simplest way to write that as an inequality. But again, we really like interval notation, so for just the heck of it, I'm just going to write down that it starts at -2, not including that, and stops at 8. Now, as we go through and do this, I want you to really think about, we're actually graphing the solution to each one of these. So again, we're thinking about what does it mean to be a solution in all of these different scenarios. So if I start a problem and you're like, hey, I think I know how to solve that, pause it, work ahead, make sure you know how to do these. This is kind of a good review and kind of a chance for you to kind of put these pieces together in your own head. Remember, we've got an absolute value equation here. It's already isolated, so we can break it into the two cases. So we get x minus 8 on this side equals -3. That represents going to the left. And x minus 8 equals +3. That represents going to the right of 0. We solve this, so we're going to add 8. So we get x equals 5. We solve this by adding 8, so we're going to get x equals 11. So we just get two answers here. So I'm going to put 0 right here. I'm going to put 5 right here, and we put a dot on that, and then 11 a little bit further out. Those right there are the answers. Nothing in between, just those two points right there. Each one of them just occurs once. So let's go through and look at this one. This was an absolute value inequality. This is a greater than, so the word that connects these is an or. It is already isolated, so here's what we're going to do. 4x minus 6, we have to switch this around, make that a -10, and 4x minus 6, we just take the absolute value off and we solve that. But we do need to remember what word connects these. If it's a greater than, it's an or, so I'm going to write a big capital or here. If it had been a less than, then it would be an and. So let's go ahead and do this one. We're going to add 6. So we get 4x less than or equal to -4. So we get x is less than or equal to -1. Again, I just divide both sides by a 4 there. I'm going to put an or here. We're going to add 6. 4x greater than or equal to 16. Divide both sides by 4. So we'd end up with, on this side, the 4's would cancel, so we'd have an x. And we're dividing by a positive, so that doesn't change the direction of the inequality, and 16 divided by 4 is 4. You do have to use the word or to write this, so we're all set there. I'm going to put -1 right here. We do have to fill that in, and we would shade this direction right here. And 4 is going to be about right here. We do have to fill that in, and the answers are greater than that, so we go this direction. And again, with the ors, any type of shading is okay, so I didn't need to be very careful about the way I did that. So there's the answer right there. And again, just for the heck of it, -infinity all the way to -1, square bracket around that, union again with starting up at 4 and then going to +infinity. And I better clean this up and make sure that those both look right. Square bracket here and then union right there. Again, didn't ask for interval notation, but not a bad idea to put it. This is one of those unique cases where we've got an absolute value isolated and it's being compared to a negative. So remember, this is nearly always positive. Smallest it could be is 0, and we're comparing that to a negative. So a positive is always bigger than a negative. So this is going to be all real numbers here. So I'm just going to graph this. Okay, all real numbers. We could say -infinity to infinity if we were going to do that in interval notation. All right. Okay, and then this one right here, similar to this one, this is always positive, and we're saying that it's less than a negative. We'll stop and think about that. Okay, a positive is always greater than a negative. That's why all real numbers work. That's why the entire number line, any number you pick there would be just fine. On this one, we're saying a positive is less than a negative. That's never true. There are no numbers that make that true. So on this one, we're going to say there is no solution. Okay. Now, I'm hoping that everybody's got this in their mind at this point, because we've talked about this so many times, probably starting a few years back. What is a solution? Why are all of these numbers that we came up with and graphed on these number lines, why are all of those solutions to those equations or those inequalities? And a hint there is we use the word true. Well, it is a number or numbers, okay, that make the equation, and sometimes I'll abbreviate that with just EQ, make the equation or inequality, and sometimes I'll write NEQ, okay, as an abbreviation for that. So it makes the equation or the inequality true. Okay, there's the key word right there. It's got to make the equation or the inequality true. So when we plug in that particular number, whether it's one specific number or two numbers that make the equation true, or a whole bunch of them in this range of answers, in this interval of answers that we got on a couple of these, it's got to make the equation or the inequality true. So let's talk about the next part. And again, these are kind of good thought questions, so see if you can think of an answer before we come up with one. Can there be more than one solution to an equation or an inequality? Why or why not? Well, if you look up above, I mean, clearly we had a couple of cases where we had more than one answer. In fact, on a few of these, we had an infinite number of solutions. There's a ton of answers here, a ton of answers there. Okay, that's every single number on the number line there. So the answer to that is definitely a yes. And then we just want to explain why. Well, it just depends on what type of equation or inequality we're solving. Okay, so it depends on, whoops, write that right, depends on what type of equation. Again, I'll just write an EQ or NEQ we're solving. And then we're going to do this. Most inequalities have an infinite number. They have an infinite number of solutions. Infinite number of solutions. Ton of answers when we have these big long ranges, these big intervals we talk about. Okay. Now, does there have to be a solution to an equation or an inequality? Well, the answer to that is clearly no, because we got one up here that has no solutions. So the answer on that one is no, and the reason for that is, so if we were to explain why, sometimes there is no number that will make the equation or the inequality true. Okay, so sometimes there is no number. There is no number that that makes the, and I'll do EQ, equation, or inequality, ineq, true. There's just not one that you can plug in that makes that equation true. Okay, now what we've been dealing with so far are all equations that have one single variable. So I'll give you a second to get that written down right here. Again, this all deals with making equations and inequalities true. So everything up here, there was only one variable. In fact, I think on every single one of these we chose to use an X on them. But take a look at these next couple at the bottom of the page. These are a little bit different, and this is where we're going to get into kind of the fundamental characteristics of something being a solution. It says find a solution for each inequality or equation. Answers will vary, and there really isn't a best way to do this. So on this one right here, it just says x plus y equals 12. Well, we just want to make that true. If we want a solution, we want to make that true. So here's what we're going to do. I'm going to say, well, let's see. Let's say that was 1. And we're going to add something to, and it's got to equal 12. Well, that means this has got to be 11. So those two numbers, an x of 1 and a y of 11, would make that true, so that checks out. We could also do this. I could do something really weird. I could say -1. Well, then I'd have to add 13, and that would equal 12. So that would check out. So I've got a couple different solutions there. So let's take a look at this one. I need to do a subtraction problem and get 12. Well, I don't need to do 2 for every single one of these, but let's just check that one. 14 minus 2, that's a solution. That one checks out. We need some numbers that multiply to be 12. 3 and 4. If x was 3 and y was 4, that would work out. If I did a 1 and a 12, or a -6 and a -2 or something like that, that would be totally okay. And then I need a division problem. I need two numbers that when I divide them, I end up with 12. Well, let's do 24 divided by 2. That would be 12. So all of those would check out. Now, we could do this a bunch of different ways. And again, answers will vary. So if you were to check your answer with your neighbor's paper or something like that, they may not have done this. They may have done 10 and 2 or 2 and 10, or maybe even a different order or something like that. The point is that every single one of those XY pairs makes each one of those equations true. So is the definition for a solution the same if you have two different variables in your equation, like these guys right here, as opposed to the ones that we did up above that only have one variable? Okay, so we talked about what a solution means here. Well, we got, an x, maybe a couple x's, maybe a whole bunch of x's. Well, down here what we're talking about is equations that have more than one variable. Well, is the definition, our idea that a solution makes the equation or the inequality true? Is that still the idea? Well, it is. Okay, so I'm going to write down yes. Okay, they still need to make the equation true. So they still need to make the equation, and I'm going to put inequality here also, the equation or inequality true. The whole point is they've got to make the equation or the inequality true. Now, if we were to take a look at these examples right here that we did on 11 through 14, how many total solutions are there for the equations with more than one variable? So we got 2 right here, but could we keep going? Could we find a bunch of different numbers that when we add them together they equal 12? Could we use decimals and fractions and all sorts of weird stuff? Well, the answer to that is yeah, there's a ton of ways that we could do this. So there's really an infinite number of solutions, okay? So an infinite number of solutions, an infinite number of solutions. Infinite number of solutions. Okay, let's take a look at the next page here and see what we've got on there. So these problems are similar to what we were just doing, except for we're going to organize these in a table, and it's asking us to find at least 3 ordered pairs that will work in each one of these. So we'll try and do this as easy as possible. I'm just going to pick some convenient numbers. Let's say we pick -1 and 0, and let's say we plug in a 2. So we know what the x is. All we need to do is make sure that whatever y turns out to be, that it would make the equation true. So if I were to plug a -1 in here, this would be 2 times -1, so we'd get -2. So let's just double check and make sure that this works. We're saying y is -2, and that should be 2 times -1. Well, 2 times -1 is -2, so that does make it true. Let's see what we get when we plug in a 0. We get 2 times 0, which is 0. And if you do 2 times 2, we end up with 4. So these 3 xy points would make that equation true. We've got 3 examples there. And then on this one, we just need some numbers that when we subtract them, they equal 10. So there are a couple different ways that we could do this. I'm going to do a 15 for x. And if I start with 15, what do I need to subtract to get 10? I need a 5. Let's start with 10. If I started with 10, I want to subtract something to get 10. Well, that would be 0. And let's say I did something like this, 5. I want to do 5 and I want to subtract something and I want to end up with 10. Well, stop and think about that. I want to subtract something and I want to end up with 10. So if I were to actually go through and solve that, I'd subtract 5. I get negative y equals, that would be positive 5. So this would be y equals negative 5. So what we're saying here is if you started out with 5, y would have to be negative 5 in order to make that work. So take a look at this. 5 minus, again, always plug in parentheses, minus 5 equals 10. Negative times negative is positive. 5 plus 5 is 10. So we'd be in good shape there. Okay, so we've got that. And then let's do the same thing we did over here. Let's use some nice numbers. So I'm going to pick negative 1 and 0 and 1 because those are pretty easy to plug in. So if I did 2 to the negative 1, remember those properties of exponents, those are going to come up again. So that would just be a 1/2. If I plug in a 0, 2 to the 0, remember any number to the 0 power is a 1. And if I do 2 to the first power, well, that's just a 2. Okay? So I can go through and I can take what look like a couple of kind of ugly equations, especially 18 and 19, and I can come up with 3 sets of ordered pairs that make each one of those equations true. So I could keep doing that. I could make a whole ton of answers. Now the question here is, why do we write the solutions as ordered pairs? Why do we always write the x first and why do we write the x second? Well, first of all, it keeps things organized. Keeps things organized. And when things get a little bit complicated, anything we can do to keep them organized is going to be really helpful. And it's also going to make it so we know this. So we know which is the x and which is y, which is x and y. All right, so if your neighbor always did y first and then x, and you kind of flip-flopped or depending on your mood or something like that, that would make things really confusing. So we want to make sure that we write them as ordered pairs. Everybody knows that x comes first and then y comes second. Now, is it possible to list every single solution to those equations? Well, like we said on the previous page, there's an infinite number of solutions to these right there. So there's no way we could do that. So I'm going to write no way too many. There's way too many answers to write solutions to all those. So this brings up an idea that you should be familiar with. We could write down all the solutions in what's called set builder notation. So we could write something like that, but that's kind of a pain. The best way to show all the solutions to an equation with 2 variables is to graph it. So let's do a graph right now. Now this is something that you should be familiar with. I am going to rewrite this just a little bit, make sure everybody's familiar with this property of fractions. There's really a 1 out front here. So what we can do is we can take the numbers and we can slide those out front so we can see what the slope is. The slope on this one is negative 1/2 and the y-intercept is 3. So this is going to cross at 3, so cross right there. And then the slope is negative 1/2. So we're going to rise negative 1 and run 2. Rise negative 1 and run 2. So it's going to look like that. So we'll get a couple points on here. We'll connect those, just draw that as straight as we possibly can. We do always want to extend that to the end of the graph and put an arrow on there, and we'll talk about why that is in just a second. But this is a really important point, and you've probably heard me say this before. A graph is a picture. You've heard that a picture is worth 1,000 words. Well, a graph is a picture of all the points that make the equation true. So it is a picture of that infinite number of points that will make that true. A picture says is worth 1,000 words. A graph is worth an infinite number of points, really. So this is why we graph these, so we can kind of get an idea what it looks like, and so we can kind of organize all of them and see what all of them would look like together. So why do we draw arrows on the end of this? Because the graph continues, because the answers continue. So right, because the answers, those xy pairs, continue. Okay? They continue off in each direction. There's an infinite number of them. They don't stop right once we get to the end of the page. Now, are there solutions to the equation y equals negative x over 2 plus 3? Are they just the integer points we graphed on the line? Okay, so just these dots that we did right here. Okay, Or are they continuous all the way along that line? So is it every single one of them in between there? In fact, if we were to zoom in here, there's really a ton of points right there, okay? Well, it really is continuous along that line. So I'm going to write continuous along that line, okay? There's lots and lots of xy pairs that make that equation true. So lots and lots of xy pairs make the equation true. So we'll say make the equation true, okay? Now, I would like you to pause for just a second and look up the words discrete and continuous. This is how you spell each one of those. You've probably heard the word continuous before. I mean, I was kind of just using this a second ago, and you may have heard of the word discrete, but if you take a second and look that up, grab your phone, grab a computer, whatever you need, look that up, see what you come up with. So if you look this up, the word discrete means separate. Separate. Okay? And the word continuous could mean a couple of different things. We kind of like to think of it as it's connected. Okay, so it's connected. And we could kind of also say that it doesn't stop. So if it's separate, the word we use for that is it's discrete. And if it's connected, if we've got a whole bunch of points that are connected together, they don't stop, they just go from one to the next, to the next, to the next, and so forth, then we call that continuous. So in this next problem, we want to just fill in the blank here. It says use the words discrete and continuous to complete the sentence. The graph is a blank string of solutions to the equation and not just the blank points we might use to sketch the graph. So the word discrete and continuous go here. It wouldn't really make much sense to say a graph is a discrete string. So let's use the word continuous here and see how that sounds. Continuous. The graph is a continuous string of solutions to the equation and not just the discrete, the separate points that we might use to sketch the graph. So the graph is a continuous string of solutions to the equation and not just the discrete points we might use to sketch the graph. Now let's use the other words, kind of the words for the definition here. The graph is a connected string of solutions to the equation and not just the separate points we might use to sketch the graph. Okay, so hopefully you've got a sense of what the word continuous and discrete mean. We will be using those throughout the year and you will see those come up again in other classes. So let's flip the page over and let's take a look at this next part. Now you probably remember from other classes that if we say solve a system of equations or we say we've got a system of equations, what we have is a set of two or more equations that are solved together. And sometimes this is called solving a system simultaneously. Simultaneously means at the same time. And one of the most basic ways to do that is to do it by graphing. So if we take a look at this graph right here, we use this for the next couple of problems. It says, how can you tell what the solution to a system is from the graph? So here's a graph. This equation right here is x plus y equals 2. That's graphed correctly if you move that around in slope-intercept form. And this one right here is x minus y equals 4. Again, if you move that around and put it in slope-intercept form, that's what it would look like. So how can you tell what the solution to that systems of equations is just by looking at the graph? Well, if this is a picture of all the points that work in that equation, and this is a picture of all the points that work in that equation, well, this right here is on both equations, so it would make both of the equations true. So what we're going to say here is it's the point, and I'll just use PT for point, where the, and I'm going to say this, where the graphs cross. Where the graphs cross. In this case, it's where the lines cross. Okay, so I'm going to put in parentheses. In this case, it's where the lines cross. So it says, what is the solution to the system? Well, the solution to the system would be right here, so we just need to count over where that is. This is the origin, 0, 0. So we go to the right 3 and down 1. So this would be 3 comma negative 1. So that would be the solution there. And it says, why is this particular point the solution to the equation? Well, it's on both graphs, so it makes both of the equations true. So I'm just going to write down on both graphs. So makes both equations, EQS, true. Again, we're coming back to this idea over and over again that when we find a solution, it has something to do with making the equations or the inequalities true. Now, if someone were to say the point 0, 2 is also a solution, so they'll agree, they say, well, yeah, 3, negative 1, yeah, I agree that that's a solution. but they're saying, oh, well, 0, 2 is also a solution. So 0, 2 is right here. If they were to say something like that, what would you say to them? Well, it's only on one of the graphs. It's not on both, okay? So we'll say this. It only makes one equation true, not both, all right? And what if somebody were to say, well, my favorite point is 0, 0. I like the origin. That's got to be an important point. 0, 0 has got to be a solution to this system. Well, this right here, it's not on either one of the graphs. It's not on either one, so it's not going to make either one of those true. So we'll say not on either graph wouldn't make either equation true. Wouldn't make either equation true. Make that look right. Equation true. Okay. All right, let's slide down here and take a look at the last little bit. I think we're almost done. All right, so it says, how many solutions do the following systems have? Well, we've got a red graph and we've got a blue graph. Each one of them happen to be lines, but these two cross right here, so this is going to have one solution, just one solution. Now this one right here, it looks like there's one line, and when I made this, I tried to make this so that it would look a little bit purple. There's actually a blue line right on top of a red line. So if you've got two lines that are right on top of each other, this point would work, that point would work, that point would work, anything in between there, anything on one line would work in the other line. So what we say here is we say there are infinitely many solutions. Infinitely many solutions, because whatever works on one of the equations would work on the other one. And then if we've got a situation like this where these two lines happen to be parallel, these are never going to cross no matter how far we extend this line in either direction. What we'd say there is there's no solution, and what we mean by that is there's no point that would make both equations true at the same time. Now, there are some vocabulary words for this that I want to make sure that you're aware of. You will see these occasionally, especially when you get into higher math classes, so let's make sure we're aware of them. So here's the vocabulary. Consistent means the system has at least one solution. It's got an answer. It may have more than one, but it's got to have at least one. Inconsistent means the system does not have an answer. It doesn't even have a single answer. Okay, so consistent has an answer, inconsistent doesn't. So these kind of go together. If it's one, it's not the other. Okay, and independent and dependent. So independent means the system has exactly one solution. Dependent means it has infinitely many solutions. Okay, so just like these two are exclusive, it's either one or the other. It's either consistent or inconsistent. It's either going to be independent or dependent. Okay, so what would it mean if somebody said, hey, I've got a system that is consistent and dependent? Well, consistent means it has an answer, and dependent means it has infinitely many answers. So what we're going to write down here is this. It will have infinitely many solutions. And then as an example, we're going to say just like example, what is that? The third example above. So just like third. Oh, I take that back. Not the third example, the second example. Okay. All right, got that one taken care of. Okay, what word could be used for two lines that are parallel? So parallel would be these guys right here. So in this third example there, they're parallel. There's no solution. So what was the word for a system that has no solution? Well, that would be inconsistent. So inconsistent. Inconsistent. All right. And last problem right here, and then you can do this little self-assessment. If a point is on the blank, then it makes the equation blank. Likewise, if a point makes the equation true, then it is on the blank. Well, if a point is on the graph, then it makes the equation true. And if a point makes the equation true, then it's going to be on the graph. Okay, those two things go hand in hand. That's something that people will often forget. They'll get stuck on a problem and they'll just basically forget, oh gosh, that point is on the graph. It's got to make the equation true. All right, go ahead and do a self-assessment. It might be a good idea to go back through and read this. There's really no extra work here. You do need to be familiar with the vocabulary and the ideas, and the fact that when we find a solution, whether it's got one variable or two variables, what we're looking for is a number or numbers that when we plug it in, it makes the equation true. All right, thanks a lot.